Hi, this is Brianette from HowRadiologyWorks.com. If you're new here, consider subscribing below and click the bell icon if you want to get notified when we release new content. What we do here is we release bite-sized content about concepts in how radiology works. And today we're talking about X-ray generation. And as we talked about before, for our X-ray tube, it basically works by shooting electrons at heavy metal and then having the X-ray photons come out. And today we're going to talk about the interactions that happen between those electrons and that heavy metal that generates those X-ray photons. So this is an example of a X-ray tube where the electrons come out here. They come out of what's called the cathode. They hit the anode. So there's a stream of electrons coming, bombarding this heavy metal, and then the X-ray photons will be coming out in this direction. But the two characteristic interactions that we're going to talk about are called bremsstrahlung and then characteristic radiation, and we're going to go through those two and how an X-ray spectrum looks and why it looks that way. So the first and the most important is bremsstrahlung, because most of the X-rays generated in a diagnostic X-ray tube are from bremsstrahlung radiation. So this here is showing part of that heavy metal. So for instance, tungsten is frequently used as the heavy metal that we're going to hit with electrons in order to generate our photons. So it'll have a nice big nucleus, right? And then also a very big electron cloud. This is just a schematic, if you remember from your high school classes, that we have our nucleus, and then these are the inner shells, and then as we go, the outer shells are less tightly bound in the nucleus. So the electrons that are coming in, it's possible for electrons to experience what's called bremsstrahlung or breaking radiation, and I'll just show that again really quickly, but essentially it's interacting between the electron and the nucleus, and the electron is getting its momentum changed very quickly, so it's going in a very different direction than it was incident, and in order to conserve the momentum, an X-ray photon is ejected. And this happens in such a way that if the electrons comes out in this direction, then the X-ray photon will come out in the opposite direction. So this can happen in a very continuous manner, such that electrons could interact just a little bit, namely they could get steered just a small amount by the nucleus, and then in that case very low energy X-ray photon would be emitted, or the electron could basically deposit nearly all of its energy into that X-ray photon. In that case, we can see that there's going to be a spectrum of possible energies that can get generated, and it's a smooth, relatively continuous spectrum of possible energies that can get generated via bremsstrahlung radiation. Then characteristic radiation is the other thing that can happen. So you have your electrons coming in, again the same instance that we talked about, but now instead of interacting with the nucleus, in this case it's an electron-electron interaction. So that electron that's coming in, it knocks out an inner shell electron, and then an electron from the neighboring shell will drop down. And if we remember from our chemistry, what happens is there's energy that's gained, or an energy difference rather, that needs to get compensated for, such that the photon that comes out, its energy will be exactly the difference in energy levels between the two shells. So in this case, the L shell and the K shell. So it's only going to be one given energy. And you could also envision one from the M shell to the L shell. So you could have one or two given energies. And for characteristic radiation, it's called characteristic because they all have that same shared characteristic that's the one given energy. Again, this is a demonstration of from the M shell to the L shell. So that another characteristic energy. So if we had just bremsstrahlung radiation, our X-ray spectrum, if it wasn't filtered, if it didn't have to pass through anything, our X-ray spectrum would look something like this, be something like a straight line, where at lower energies we have more X-ray photons, and at higher energy we'll have fewer X-ray photons, because it's less likely to have those interactions where the electron transfers all of its energy to a photon. But then in reality, what ends up happening is we start with something like this, and then we have filtration. We have to pass through the glass window, and then we also usually have additional filtration of the X-rays before they get to the patient. So those lower energy X-rays are preferentially attenuated. So you get something that would look like this if you have just bremsstrahlung plus filtration. Then if you add those characteristic peaks, you get something that looks like this. So when someone shows you a plot that's energy and the number of photons and talks about this fancy thing called the X-ray spectrum, you can just remember that it's not really that complicated. There's just two fundamental things that are happening. One is that bremsstrahlung and the other is the characteristic characteristic radiation. So we talked about bremsstrahlung and characteristic radiation, and those are the mechanisms by which X-rays are generated that are used for diagnostic X-ray imaging and diagnostic CT imaging. Again, this was Brian Nett with HowRadiologyWorks.com. Thanks again for watching. Again, this has been Brian Nett with HowRadiologyWorks.com. Let me know what your favorite part about the X-ray generation process is. Is it the boiling off of the electrons, or electrons hitting the heavy metal, or what? Just the fact that bremsstrahlung is a pretty cool word. So also head on over to HowRadiologyWorks.com/XrayGen. That's X-ray and then GEN for X-ray generation. You can download a PDF cheat sheet that has just in one place the information that you need about X-ray generation and the X-ray tube. Again, thanks again.